Hello and welcome to our lecture series, Introduction to Research Data Management. Before we start, let's recapitulate why we should bother with research data management. First of all, we can see data becomes the new oil, as they say, or data, we can see it as a foundation. So if we look at many properties, we find that they are inherently stochastic. That means we need to model them, for example, via statistical modeling, or we use machine learning or artificial intelligence or something. This requires that we have large data accessible. Otherwise, we can't train, for example, a machine learning model. However, we also want to focus on more meaningful work. So we want to capture all this data easily. We want to automate our workflows and share data amongst research groups. In other words, we can get more out of the little data that we have. We also need to think about data quality control. There is a fun fact that you can look at down here. If you ask data scientists and companies what they spend their time on, and they focus on 80% of the time on data science in terms of capturing data, cleaning data, processing data, and less than 20%, and that doesn't include any meetings, less than 20% of the time is spent on actually training models or building new models. So apart from this aspect, we also want to make our science more reproducible, so that we need to document which samples we used, we need to document the tools that we use or the software environment that we use for analysis. We also want to define standard operating procedures, like how we perform our measurements and how we do our data quality control measures. All of this requires extensive documentation. It's part of data management. And last but not least, there's external pressures, because funding agencies require these days that you have a plan for research data management. So where does all the data end up? Most of it will end up on your local PC. It's not really good, is it? There are a lot of databases that we can use, or the local or institute network. Many try to store the data into the cloud or an HPC cluster. So all of this is rather disconnected, and we need to explore how we can bring all of these data sources and data storage systems together. So there's one side, the technical side to it. Let's quote the DFG rules first. So following the rules of the good scientific practice, research data should be stored for at least 10 years. So that means we need to have technical systems that are guaranteed to be there for at least 10 years. So which technical systems do we have available, or do we need to build some? What happens beyond those 10 years? Will this data be useless? Will it be deleted? Will it be given to the community in a different repository? How safe are our data? What happens if a system fails? That can be something like an accident, but it could also be a fire in our compute centers or a water damage in the cooling system. What happens in these cases? We need to think on a large time scale of at least 10 years. There's also the non-trivial aspect of, can we actually access the data in more than 10 years? We can maybe store them now, but can we retrieve them in 5-6 years? That also implies the question, can we even read the file formats that we have now? There's also an organizational side to it. We said that we need to store the data for at least 10 years. So who does this? Who is there for 10 years? Or is it a chain of people that will be responsible? Is there a handover planned? Who knows in 10 years which data are stored where? People tend to move between academic institutions, or go to industry, or come from industry back to academia. How do we make sure that the information remains accessible? So what do we need to store? There's first of all information about the experimental samples themselves. So we have the physical samples those need to be stored, for example, in a safe storage location. But we also need to track how these samples were created, or what's in those samples, how we prepared them, if there are any mechanical tests or anything else happened to those samples. We also have a lot of scientific instruments, so we need to track which make and model we have, and all of those scientific instruments will operate on some sort of software. So we also need to track which software was used at which time. Then we have the experimental data themselves. So we have typically raw data that will then later be processed and analyzed. So we have derived data that we also need to store. And more analyses are done using software. So we have software code that we need to store somewhere. We have analysis code that we need to store software. And we have the environment in which the software runs. For example, we may have a Windows 10 PC that nears its end of life. So how do we run the software in 10 years? Or do we have maybe a Linux or Unix environment? How can we make sure that we preserve the environment for more than 10 years so that when we want to access all of this software or the data, we can actually do so? In this research project Elixir, they proposed this nice data life cycle that we can look at in more detail, which data comes along where. So before we start our analysis, we need to plan how we capture the data, what kind of data we have. Then we collect the data, process the data, analyze, preserve it, share and reuse. Let's look at all of these steps in a little bit more detail. So when we plan, we need to look at what data are being generated and which data are being used. Which file formats are we going to have? Where do we want to store these files? Which storage systems do we have? Do we need to think about data access and data security? Which part, or all of it, of the data do we want to share? What costs are involved in processing the data, storing them, or sharing them? What kind of relevant metadata do we have that describe the data? Are there any legal aspects that we need to think about, or any ethical requirements? For example, if we have personal information there, the GDPR will put stringent requirements on what we can do with the data and what we can't. So this stage is where we write a detailed data management plan. In the next stage, we collect all the data, so we conduct our experiments, for example. So we have our scientific instruments, and do the measurements. We can also have maybe questionnaires or polls. Here we need to consider what quality the data have, how the data comes about, the data provenance, all the technical aspects, like which data are stored where and so on. And we also need to collect relevant metadata to describe the data that we have. In the next phase, we process the data. Again, we need to think about data quality and pre-process our data for later analysis. We should also start to think ahead, so we can bring the data into a format that is readable later on. A lot of scientific instruments store the data in proprietary formats. For a long-term perspective, this is not ideal. We may also start our exploratory data analysis here and other tasks. Now we analyze our data according to the project requirements. So that also means that we need to maybe revisit the planning and acquisition of the data as new insights emerge. So we need to be prepared to step back into the cycle. After our analysis is complete, we want to future-proof our data. So we want to preserve the data that we have and the analysis chain as well. So ideally, we would convert all the files into an open file format, and we need to think about how we preserve the analysis environment. Think about how we can access not only the data themselves, but also the software in more than 10 years from now. After this, we are ready to share our data. So we need to think about which part, if any, of the data can be shared with the community, which data are valuable for the community, but also what kind of data do we want to share. Remember that we all stand on the shoulders of those come before us, so the more data we can share, the more others can make use of our research. This leads us to the reuse of data. So in our own perspective, it avoids unnecessary and costly experiments, but we can also analyze different aspects of the data and, for example, merge our data with other data. We can also get more credit for our work, of course, but it also enables meta-analysis that analyze all the data and the analysis of the data that are already there and gain new insights. So how do we get there? we need to think about open and what's called fair data. So we need to make our data findable. That means we have to have persistent identifiers that point us to the data, even if the underlying systems change. We need to publish our data in data archives, for example Zenodo or others. We also need to describe our data. That means we need to provide relevant metadata that describe the data. What are the data about? How was the data acquired? Which instruments did we use? Which measurement protocols? Which samples? And so on. And in the end, we need to have open data, so non-proprietary file formats that can be read by anyone. We also have to have a reproducible software environment. It's not enough to say that we use a specific software. We need to think about what happens, for example, in 10 years. How can we run this specific environment? This is what's called FAIR data. FAIR is an abbreviation for findable, accessible, interoperable and reusable data. In more detail, you can see here all the FAIR principles. So data becomes our new resource. For example, simulation, model analysis, machine learning and artificial intelligence, they all require data as their input. If we want to build data-centric workflow, we need to have data and software as one part of the overall aspects. We also want to exchange and reuse data for new insights and share with other research groups, so that with time we have more data available, for example, for advanced machine learning techniques. The way to get there is fair and open data. So we need to make our data future-proof. We need to publish our data in archives, describe it with relevant metadata, and include our software environments. As a benefit, it also makes our science even more reproducible. We define how we acquire the data, which instruments we use, we track our samples, we convert to open file formats, and so on. This automatically means that we also comply with the funding agency requirements and best principles. The FAIR data principles and open and the data cycle help us to identify which actions we need to take.